just going to talk really fast and make up for the time. No. So welcome you all to the 14th annual workshop on Charm++ and its applications. We've been doing it for roughly 15 years, I think, even though it's the 14th workshop. And increasingly great external speakers and overall program. This year we have had a little bit of an issue with scheduling, so many DOE folk could not come, but we're hoping that it's still a very productive workshop. So what I usually do at the beginning is give you a little bit of an overview for some new people that are here about what our group does and the Charm++ programming model, and then give an overview of what we did over the last year, a little bit of highlights, and then, of course, there'll be a bunch of talks that will elaborate on those anyways. So task models are quite in vogue these days, and this is the slide that I picked last year, but I think it's valid still to speak of this. So people were going from MPI to MPI plus X, and that X was OpenMP typically, and then now they're thinking about task models as well, but the task models are part of OpenMP as well as other things. So asynchrony and task models are in vogue, but I think there is one more fork that the community needs to take, and that fork is over decomposition and migratability, and that's the one that we have been on for a while. So that what are these ideas? Over decomposition simply means that we want the programmer to decompose their computation, which is work units and data units, into a large number of pieces, independent of the number of cores or hardware threads or hardware resources in general that they have, so that they leave the assignment of those to the runtime system. So this is not so hard. We do decomposition anyways. We just overdo it, like I say, and so then, okay, what's the next piece? Well, the next piece is these pieces must be made migratable. The runtime system should not only be able to assign them initially to processors, it should be able to, it should be free to move them around to different nodes in the system as needed by the runtime conditions. And this, for the app developer, the consequences are simply that the communication must now be addressed to logical units. Those are the ones that you over decompose the computation into, but not to physical processors. Don't make a reference to physical processors. Remove physical processors from your ontology. That's the message for the app developer, which is not hard. In fact, it's easier because you write things in terms of logical units. But the consequences for the runtime system are significant because now it has to keep track of where each unit is as the program runs, and that involves naming and location management. Every entity that's created has to be given a unique name, and its location must be tracked scalably and efficiently. The consequence of these two decisions, and one that we keep enhancing through the programming model, is asynchrony. And so this shows up in Charm++ as a message-driven execution. So you have many units on each processor. They address each other via logical names. So there is a need for scheduling. And the question becomes, what kind of scheduling? Who should control the scheduling? Who should control what runs on a given processor? And one answer is let the programmer decide, which is the traditional answer in the HPC community. But so, for example, in AMR framework, there are many things that are happening, and the programmer is controlling what should happen next. But message-driven execution basically leaves that decision to the runtime system, gives you one more degree of freedom to control the execution. So Charm++ actually embodies these ideas. It began with an adaptive runtime system for task parallelism, state space search, and so on. But in the 90s we moved to the dynamic or irregular but iterative applications, science and engineering applications. And this is a feature that all of these features that we talked about turn out to be useful for future hardware even more. So we're kind of there to meet the future, as it were, just because of some lucky or maybe insightful choices we made over the years. Just a picture to reinforce the programming model, at least the under the hood look. a program consists of a large number of objects shown by the squares here, decomposed over a set of processors. And when that little peach colored object on the left wants to invoke a method in a particular thing, let's say a particular object a square bracket 29 dot foo, well, the system packages those method invocations into this little orange packet, figures out where that lives based using its location management, and all that happens is that method invocation goes and sits on the destination processor's scheduler queue. At some point, that processor picks up that, it comes to the head, it checks if the object is still there because it might have migrated away, and if not, it will, if so, it will forward it. Otherwise, it invokes the method. That method runs to completion, generating maybe other messages for other objects in the system. So this is kind of the entire programming, the message-driven execution paradigm in a nutshell. So these three ideas give rise, along with introspection and adaptivity, give rise to an adaptive runtime system with which you can do all kinds of things, as we'll see throughout the workshop, for dynamically balancing loads, optimizing communications, resilience, and prefetching, and variety of things like that can be done. And this is a model that we have been elaborating on and developing applications for over the last 15 years for sure. Well, let me skip this picture. These are the components of the runtime system that you will see various talks on. We have the load balancers. We have management of index collections of objects. These are work units and data units, and the scheduling for that, which is at the heart of the thing. You'll hear a little bit more about the scheduler in the Argo talk. And using this with introspection interface, where the user doesn't have to be involved in writing any introspection, the runtime can introspect and do a variety of strategies that optimize load, communication, or induce or tolerate faults, and so on. So a few highlights from the last year that I just want to mention. We have 4 major applications and maybe a dozen other applications. These 4 are collaborative and ongoing for last 10 years, and they have scaled to hundreds of thousands of cores. Changa for astronomy, NAMD, one of the oldest applications for biophysics. Pisum, which is a simulation of epidemics, and OpenAtom. These are all current or past or upcoming PRAC applications. PRAC applications are selected by NSF, not by the NCSA, but NSF for large allocation on blue waters. And so it's a measure of their success that they're all PRAC applications scaled to that large machines. You will hear about a couple of them in the talks, but I'll summarize maybe 1 or 2 here. So Charm++, one of the things that happened last year was there was a lot of external evaluation of Charm++. One of the most extensive one was carried out by Sanjay. And that's a team led by Janine and many people in the Dharma team there at Sandia, at Livermore, and so on. So Charm++ was selected along with Legion and Uinta for this week-long intensive exploration by them. Actually, the week-long was one part of that, where in a week they implement, a bunch of people come together and they implement Mini Aero, which is their mini app, using Learn Charm++, Learn Uinta in the other week, and so on. And so they were. This was very successful, and many errors implemented with load balancing, resilience, etc. In that time, you can read about it in the Sandia report. Intel has been exploring Charm++. That continues. You'll hear a little bit, hopefully, about that from Robert Wingard's and presented probably by Maria Gerzeran today. Episymdemics, we're not going to have a talk about it, but there's been a lot of activity on this, and you can imagine in the last year there was a lot of attention paid nationally and internationally to epidemics, and this is a discrete event simulation with a very detailed model of users, their behaviors, places, and people to see how epidemics spread. So the original code was in MPI. Several years ago, it was converted to Charm++. And recent results that I'm not sure I should talk about, they're just submitted to, they were recently submitted to conference. So these show excellent scaling to blue waters and other machines that involve many optimizations that exploit the asynchrony in particular, as well as load balancing. And this is a collaboration with Madhu Marathe and other people at Virginia Tech. As you know, CharmWorks, I mentioned last year, that was starting, that's a startup that is doing commercialization, well, basically commercial support of Charm++. The idea is that the company will focus on 10 to 1,000 nodes mostly, not exclusively, but that's the market, that segment that is mostly focusing on. And then the university version will continue to be distributed as before, freely in source code form for nonprofits. The code base, we are committed to bringing back most of the things, pretty much all of the things developed at CharmWorks into the code base that's available for everyone. Some of the things that we did last year are ongoing, are an Eclipse plugin, improvements to the GUI-based debugger called Charm Debug, robust parsing of .ci files. This was one of the things that was identified by the exploration of the Intel guys, that our users are much too forgiving because they write their interface files once, battle with the system, and then move on to, once they have learned it, move on to just developing their application. And so we never improved the parsing of CFI's error messages, etc. So that was significantly improved. Already GPU manager, I'll just pick a few, that was developed here. Many of these things are research ideas developed here that were then being refined and made more robust at CharmWorks. And so several things like that. There is now a performance report automatically being generated, for example, and a lot of emphasis on automatic choices of default parameters, so the programmer doesn't have to spend a lot of time doing reasonable initial choices for parameters. So, so one of the biggest contributions for the last year, the products of our lab for the last year, is really our graduate students. We have 5 PhD students graduating this year, which is kind of even unusual for even us. Between January, when the spurt started, to the middle of the year, I expect there to be 5 people graduating. Nick Hill, who is at Livermore now, just left 2 days ago. Jonathan Liflander is at Sandia. He will be here tomorrow. He will be joining there in June. Xiang Ni, who is going to IBM Research Yorktown Heights. Phil Miller, who will be going to CharmWorks. Harshita, as yet unspoken for. So, so this is actually a big, if at all I want to characterize one thing that's going to happen to the group in the next few months, this will be one, because this is really a talented set of students that are all graduating within a short span of time. So a lot of pressure on the rest of my students to pick up. So in the workshop, you're going to hear keynotes from Barbara today and Thomas Sterling tomorrow. We have several invited talks and application reviews. We'll learn about many features in Charm++ that are added. In particular, today you'll hear about within node parallelism and AMPI this morning. Tomorrow there is a panel on higher level abstractions. And so it's a program packed with interesting talks and updates on what's going on in Charm++. It's meant to be interactive, so so please feel free to stop and ask questions during the talks. We're trying to keep to the schedule, you know, plus minus 5 minutes is okay though. And yes, and so so with that, I will stop my talk. And are there any questions? All right, thank you very much.